is not easy to explain the origins of power of quantum computer. Many people try to do this in a simple language, and I myself made many efforts in my life, but it always appears something in between the simple but wrong explanation or correct but too complicated. Why is that? Well, I don't know. Maybe quantum computing is quite a complicated subject. So, I invented my own approach to this explanation. The best and the most rigorous way to describe the powers and weaknesses of quantum computing is to give you the mathematical model of quantum computing. But it is so much math, and it is so complicated, and it requires so much time. No, I'm not going to do that. Instead, I will assume that we already have the mathematical model. We take it for granted for now. Physicists invented it, why wouldn't we trust them? And from this mathematical model, we will pick out the demands for the physical process that it describes. So instead of learning and describing a quantum system, which requires a lot of knowledge and experience in physics, we are going to go the opposite way. We take the description as an input. We know that it works for the quantum algorithms, described in the introductory course, for example, and we deduce what kind of a process, physical process, can meet the requirements of this mathematical model. This will help us to understand the nature of a quantum computer and the main obstacle in its implementation. Now, if you don't know the mathematical model yet, don't worry. You can trust me about my reasoning for now, and you can learn and check it later. 3 demands to the computing physical process, which I deduced from the mathematical model, are: the first, continuum of states; the second, true randomness; and the third, and the last one, is the interference. So, if we want to build something as powerful as a quantum computer, we have to meet these 3 requirements in our implementation. In the next videos, I'm going to explain these requirements one by one. Let's start from the first.